All right, good morning, guys. So, in continuation to our previous session, we were discussing about combination logic gates. Here is an example, a bit more complex example. As you can see on your screen, we are using a total of 5 logic gates here. So, this one is AND gate, this one is NOR gate, another AND gate here, and another NOR gate. So, and you can see we are dealing with 3 inputs here, and there is one final output X mentioned here. So the reason I'm showing you this example is this truth table. You can see this truth table. It has many columns. First 3 columns are for the input A, B, and C, and the output, as you can see, X is the final output. So the last column, X, this is your final output. This is the final output of this whole combination uh, logic circuit. In between, you will see some other columns like D here, E, F, G. These 4 columns are the, you can say, the transition stage output. The in between, there are, I mean, after this gate, the output we named it as D. This gate, NOR gate output, we named it as E. So you can write names for output of each gate, and for that each output you can make columns here. That will be I mean, it will reduce your effort in a case that you will not do a mistake in finding out the final output. So it's better to make the columns for each step in between, and write it down here, and from there you can easily trace what is the final output. Otherwise, this logic thing, where it was 0 or where it was 1, if you do it verbally, then it will be a problem, and you can lose track where you were, what was the logic. So anyway, so 3 inputs. You can see there are total 8 different input combinations. So there are 8, you can count it. First one, obviously you start with the 0 0 0, all 3 0. Then the C, the last one, you make it 1 while others at 0. Then you make B as 1 while others 0. Then you make both B and C as 1 1. Then you make A as 1, then others 0. So you are actually considering C as a least significant digit. You and A as the most significant digit. You can keep on increasing the combinations here. So after 1 0 0, you can do it 1 0 1. So from here, I mean, keeping this A as 1 from here onwards, because here you have used all the possible combinations with A at 0. Then you start with C as, make it 1, then make B 1 while C at 0, A still as 1. Then last combination will be all 3 as 1 1 1. So another easy thing would be, if you can see that C input is changing alternatively between 0 and 1. You can see the first one is 0, then 1, 0, then 1, and it will continue like this all the way. The B input is changing after every two steps. See, first two inputs are 0 0, then 1 1, then 0 0, and then 1 1. Okay, and now coming to the input A, total there are 8 inputs, 8 input combinations. So look at A now. First 4 are straight away 0 0 0 0 0, and the last 4 are straight away 1 1 1 1. So this way also you can write all the 8 input combinations. Okay, do it either horizontally as I told you before, or do it vertically as I told you now, that just when you are writing C inputs, just write 0 1 0 1 0 1. When you are writing B inputs, write 0 0 1 1 0 0 1 1 in pairs. And when you are writing C inputs, first 4 0, last 4 1. So this will make your 8 possible combinations. All 8 combinations will be completed. After that, you can simply use the logic. The first we have to fill the column for D. D is actually A multiply B. So you can see here D output is actually multiplication between A and B. So just look at the first row, A and B. If both are 0, the output D will be 0. You can see it here. So it will be only 1 when both A and B are 1. So you can see where both are 1. So they are in the last two combination, the both are 1. So you can see the D is also 1 in only last two combinations. Before it is all zeros. Now the E output here is the output of this NOR gate. And this NOR gate is dealing with input B and C. Okay, so you have to be careful. You have to look at which inputs it is dealing with. It is dealing with B and C. So now you have to look at these two columns B and C in the truth table, and from there you need to write column E. Because it is a NOR gate, it is, remember, this is NOR gate, it is not OR gate. OR gate has no bubble here, but this bubble, as I'm pointing out, this bubble represent a NOT gate here. So a combination of OR gate and NOT gate becomes NOR gate, N-O-R, NOR. So it will do addition, but then it will invert its output. So which you will see here, B and C, first input you see B and C, 0 and 0. So its answer should be 0 if you are doing a simple addition. 0 plus 0 is 0. But because it is not OR gate, it is NOR gate, N-O-R. So what it will do, the NOT gate will inverse the output. It will make it 1. So 0 plus 0, it will give the output as 1, as you can see. I am pointing out here. Next combination B and C is 0 plus 1. So 0 plus 1 should be 1. But here it is giving 0. The reason, same reason, because it is giving the opposite of the possible output, because it is a NOR gate. There is a NOT gate active on the output. So similarly, you will fill out all this column. And then F is simply multiplication between B and C. So you just look at the B and C combinations and fill out the F column. And G column, again, G is the multiplication between E and F now. So output of NOR gate and output of this AND gate. So E and F, this is E and this is F. So these two you have to multiply and fill out the column G. And then finally G and D are going into the NOR gate. So just look at G and D. D is here and G column is here. Looking at these two inputs, you can fill the final output column, which is X, and look at the gate, that this is a NOR gate. So you need to inverse the output. So that's how you can make a truth table. After a practice of, if you do practice with 2 or 3 different truth tables, you will be doing it very swiftly. It's a simple thing, just needs a logic, and you can easily fill the truth table. Looks like a big truth table, but you can easily do it by just looking at the gates combination and using the basic logics of multiplication and addition and inversion. So this slide was in continuation to our topic and discussion. So I'll go back to the chapter 2. We have to start the chapter 2, which is about combination logic circuits. The first topic is about ICs. We have already discussed some basic information about the ICs, but here also there is some useful information available. As you know that IC stands for integrated circuit because it's a combination of many components. An IC is a tiny circuit made up of resistors. There could be what components could be there? There could be resistors, diodes, and transistors. They are all placed in a single package. And that single package is very small in size. So each IC has a part number. To identify ICs, if you look at these ICs in the bottom right corner, so you have seen similar ICs in the lab as well. So if there are various ICs sitting in the lab, all of them would look like the same. So how to identify them? On each IC there is a part number written. That part number is the identification of that IC. Like for us, we used to have Emirates ID. On that Emirates ID there is a specific number. That number is your citizenship number. So from there the government identified which person and your location, address, all the details are identified by that number written on your Emirates ID. Similarly, the number written on the IC, it will identify what type of IC is this, what it can do, what are its properties, everything. So ICs are available in different packages. The photo below shows from left to right an IC that contains logic gates packed in a 14-pin package. So this IC here, on which I am pointing out, this has a 14 pin, 14 legs. A timer IC 8 pin in the middle, and a voltage regulator IC in a 3-pin package. This IC should be familiar to you once it is written here that is voltage regulator IC. I hope you remember you used a voltage regulator IC in your project in term 3 of certificate when you were making a regulated DC power supply. So you used a regulator IC in that project. Maybe from a picture you can recognize. So the part number will tell you whether it is the IC or transistor in this package, what type of IC and what type of transistors are available in there. This is okay. Now you don't remember all the part numbers and their properties. So what you can do, you can you can do this by looking up the part number using a research engine on the internet like Google. Just Google it and it will show you the uh, data sheet of that particular IC, or it will take you to the manufacturer website. Or if you know the manufacturer website already, so all ICs are marked with the part number. So or you can check that IC number direct on manufacturer website. All ICs are marked with the part number, no matter in which type of package they are packaged. So every package you will see definitely there is a part number. Otherwise, no one will be able to identify what IC is there. So I will not read out all this. I will see there is a diagram on the bottom right corner. This is a IC. How many pins? There are total 8 pins. To identify which pin is number 1, so there is a notch available. Can you see a semi half circle? A half circle is here. So this circle shows you if this circle is on your left, then the bottom left pin is number 1. So remember, I will repeat this notch. Sometime on some ICs there is a notch or a half circle here. Sometimes there is a dot here, a round dot you will see. So if you put that dot on or this notch on your left side, then the bottom left pin will be number 1. That pin number will be 1, and sequentially it will go on 2, 3, 4. From 4, next number is 5. 5 will be top right corner. So top right corner will continue to 5, 6, 7, 8. So that's how all the ICs, any IC, any manufacturer, any brand. So you will pick it up, it will follow the same number pattern. Okay. So here is a timing diagram. You know, in ICs, there are logic gates available, and those logic gates are getting input A and B, depends how many inputs you are dealing with. In this example, we are dealing with two input signals A and B. So the logic gates, they are getting input A and B, and they are giving you output based on their combination logic. Now the question is that logic gates have to work very fast. So the input A and B should also change very swiftly. So to, to change the input A and B, because if you have to apply four different combinations, because if there are two inputs, then you will have four different input combinations. All of this operation should finish not in seconds, not in milliseconds, but in even nanoseconds or even less than that. Nanosecond is very little time. So there are timer ICs, and they are giving the timing pulse. Based on that timing, you can see on top T0, T1, T2, T3. These are the timing pulse. The timing IC are giving timer their timing pulse. Whenever the timing pulse is coming, the input A and B are changing its state. The 0 will become 1 or 1 will become 0. In the same way as we write the truth table and we develop different input combinations. So if the timing pulses are coming very fast, the input A and B will also be changing very fast. And if input A and B are changing very fast, your output will also be coming very swiftly, fastly. So this whole process is very quick. It finishes in nanosecond. So now look at here. This is high state. A is at high level now. Okay, then it is low here. It is low here again. Then it is high here. So at every timing pulse, either input A is changing state or input B is changing state. So this graph is representing that how it is. Why we are writing these are the transitions. All of these are transitions. Transitions means the timing pulse. At every timing pulse, input A and B, any one of them or both of them, they will change their value from 0 to 1. And exactly uh, same time, the output will also change. So now look at these function gate output signals. If the one of the gate is giving us some multiplication A dot B, so you can see this is at low level. Look at this 0. 0 means this is at low level. Why it is at low level? Because you can see that B is low, A is high. Any one of them is low, the output will also be low, because that's what's happened in multiplication. So you will see that this first function, it is giving at every transition at time t0, at time t1, it is again 0 because B is low and A is also low. At time t2, it is again low because B has gone to 1 but A is still 0. So that's why its output is still 0. Now here at t3, look at this. At t3, we see a change that this function has now raised to 1. It is high output. Reason? Because now at this point B was already 1 But A has also changed its state at T3, transition T3, it has also become 1. So when both input A and B are 1, the output is also 1. Then at T4, you will see the output is again 0 because the B has become 0 here, while A is still at 1 continuously after that. But B is at 0, so the output will also become 0. The same way you can trace other functions, and you can see depending on the input combinations how the output graph, you can say, or output state is changing based on each transition, each time T0, T1, T2. It will continue like that. This is an example for you to look at. You can consider this example in your own time. For practice, you can just take the function which is written here on top and try to make a logic circuit from your own thinking, and then later on match with this, that whether you have come up with a correct logic circuit or not. Or you can do the reverse practice. The solution is here, the function is also given here, and the diagram is also given here. So anyway, now in this logic circuit, if you count, there are 1, 2, 3, 4, 5, 6 logic gates. So there are 6 logic gates, and finally you are getting an output which is called F here. In the next slide, and this is the truth table for that. This slide is very important, guys. This shows that whatever you are getting from this combination logic circuit, you can reduce the number of gates to only 4 here. Here there were 6 logic gates. Here there are only 4 logic gates. These two logic circuits are doing the same thing. How they are doing the same thing? Depending on the input combinations, the output G and output F are behaving the same way. Okay, the final output is the same. If you look at the truth table, this is the truth table. So F output is mentioned here and G output is also mentioned here. Both are exactly the same. In the blue columns, you can see there is no difference. But for output G combination circuit is like this. For output F, the combination logic circuit is like this. So if I ask you a question, which combination logic circuit is more suitable? Can someone answer? F or G? Yes, guys, I'm asking you a question. Please tell me which combination logic circuit is more suitable. No, Abdurrahman, F is not suitable. The reason, because as I told you in yes, G is more suitable. Why? I give you the reason. See, we are dealing with digital electronics, or we want that simple logic is, if there are more components available, if there are more components, what will happen? They will take more, they will consume more energy, and it will take more time to give you the final output. Because for each gate it will take some energy and it will take some time to produce output. So the output F, you will get output F after using more space, using more energy, and using more time. And all these three things, if you just think about your mobile phone, you don't want all these things in your mobile phone. You want your mobile phone to be having very less size. The motherboard or the microprocessor should not occupy more space. Less size ICs. You want its energy consumption to be very low so that you can use it all day without any trouble. And third, you want the output response very fast. Okay, so anything which is possible in 10 nanosecond, you want it to do in 1 nanosecond or even less than that. So all these three things, these three examples are more possible. They can, the G output, this circuit can do it in a better way because it has less components, it will consume less energy, it will use less time, and it will give you output quickly. Output G will be more quicker than F. So that's why uh, this is more suitable. And whenever you are making an IC, you want to increase the number of components. You want to put as much as components possible on a small IC package so that you can uh, compact more circuits into a smaller space. So if you can reduce the circuit size, so you will be able to accommodate more circuits on the IC package. So these are the reasons why this G circuit is more suitable than F. Okay guys, so I will stop my lecture here.